Hello, and thank you for your interest in learning about measurements that can be taken on-site and incorporated into carbon planning. In this presentation, we will be reviewing some of the on-site carbon measurements you can utilize to better estimate and monitor carbon stocks. The carbon cycle within agricultural operations is complex and dynamic, but it is important to understand when trying to estimate the carbon stock on farms. Agricultural systems can be both a source and a sink for greenhouse gases. Greenhouse gas emission pathways on farms can include the fuel needed to run equipment, methane released from livestock, greenhouse gases released from fertilizers, greenhouse gases released from the soil following tillage, and released from organic materials as they decompose. Farms also store lots of carbon through the organic matter added and retained in the soil over time, the carbon taken into plants through photosynthesis, and the woody biomass managed and maintained on farms. Every farm is unique and will have its own unique carbon footprint. The measurements we will cover today will focus on carbon. There is so much more information to read and consider on the greenhouse gas cycle on farms, and to think if an individual operation is a sink or source. This image is from the Council for Agricultural Science and Technology's page considering the potential for U.S. agriculture to be greenhouse gas negative, and further describes these carbon cycle pathways on their website. The Center for Technical Development in Washington State Department of Agriculture's Danny Gilardi created an informative video that provides an overview of soil carbon in agriculture with an emphasis on our current scientific understanding of carbon dynamics. Soil Carbon Science 101 is publicly available on the CTD website or YouTube channel. On-site measurements are most beneficial when you have a landowner who is really interested in measuring and continuing to monitor the carbon or biomass on their land. On-site measurements can also be helpful as a baseline to compare to modeled data. Taking on-site measurements can be time-consuming, but are the best way to get site-specific information and begin to understand what is happening above or below ground. You probably won't do these tests at every site, but we wanted to take some time to share tools and resources available in case field measurements are desired for your planning. Most often, modeling tools such as COMET are used to estimate the carbon benefit of conservation practices. Below ground, field-based measurements to assess and monitor carbon include measuring organic matter, measuring the bulk density of your farm soil, and measuring the microbial respiration. Above ground, you can also take measurements to consider the carbon stored in perennial and annual biomass. Tracking these measurements over time can inform whether a management system is resulting in increased or decreased carbon levels within a particular area of an operation. To know whether a soil is acting as a carbon sink or source, you need to measure soil carbon and repeat this measurement over time. There are two overall forms of carbon held in soil, organic and inorganic. Soil inorganic carbon is formed from the parent material through the weathering of rocks and minerals, or is from the reaction of soil minerals with atmospheric CO2. This is an uncommon measurement, and methods are still being developed to measure this precisely. Soil organic carbon is what we typically measure and is derived from living organisms that have undergone or are undergoing decomposition. Organic matter, which can be representative of soil organic carbon, is commonly reported on soil tests. Organic matter can be anywhere from less than 1% to over 10% of a soil's volume. Organic matter is a dynamic property of soil that will change with how a soil is managed. This makes organic matter an area of opportunity to increase the carbon sink capacity on farms by trying to increase and maintain the organic matter present throughout the soil profile. Beyond just the carbon focus, soil organic matter influences the quality and function of a soil by promoting aggregation, fueling microbes for long-term nutrient cycling, and maintaining a structural balance between the mineral, air, and water within a soil. Soil organic matter is a test offered by many soil labs. The Walkley-Black method is commonly used to measure soil organic carbon. You can see the WB by the organic matter test result reported by Soil Test Farm Consultants. Labs assume that soil organic matter is 58% carbon and use this conversion to take the measured soil organic carbon and report it as organic matter. For carbon planning, we often want to see the soil carbon value to estimate soil carbon stocks. We can convert the organic matter percent back to soil carbon by multiplying the percent organic matter by 0.58. There are other lab tests that may be available for measuring soil carbon, but in general, these are less commonly offered. When taking a soil sample to send to the lab, you want to make sure you are taking a representative sample. In general, you want to take a composite sample across a field that has the same soil type and same management. A composite is taking multiple smaller samples across the whole test area, mixing them together, and then using a small part of that mixture for testing. Additional resources to determine your sample areas will be shared later on. Organic matter varies greatly with depth. Make sure to be consistent and take good notes so that if you, the farmer, or your organization decides to test organic matter again, they will be able to get a comparable sample. Bulk density is another site-specific measurement that is needed to accurately estimate the soil organic carbon. Bulk density is the mass of a soil within a volume. It tells us how much air and pore space is present. We want to accurately represent how dense a soil is, as it will affect the calculation of soil carbon stock. When soil organic carbon stock is calculated, you multiply the percent organic carbon of a soil by its bulk density, by the depth we've sampled, by the area of the field being represented. There are spreadsheets available to calculate this for you. Bulk density varies with the particle density, which will have different values for a sandy, silty, or clayey soil. This is where site-specific sampling can greatly improve the carbon estimates for carbon planning. Different soils have their own inherent ability to store carbon depending on their mineralogy. Bulk density is also a way to measure the compaction of a soil. Soils with a lower bulk density have more pore space and aeration. We've briefly discussed what bulk density is and why it is needed for carbon planning. If you would like to learn how to take bulk density samples yourself, WSDA has great videos and written instructions available. Point Blue Conservation also has a written procedure for bulk density sampling. If you or your district has participated in the WSDA State of the Soil Sampling Program, WSDA gave your district bulk density sampling equipment. Access to this equipment has made it a viable test to continue to offer for farms. The processing of a bulk density sample can be done at your office if you have access to an oven to dry the sample at a low temperature to not burn or volatilize the carbon, and a scale to weigh your samples before and after drying. Carbon fuels biological activity in the soil. If we have an active soil microbial community, we will have respiration. Soil respiration is something that we can measure and monitor to try to understand how carbon is cycling through the soil and connect that cycling to the environment or management conditions. There are test strips that can be used in the field to measure the soil respiration. NRCS has a publication further describing this test. Above-ground perennial biomass is another important metric to consider when carbon planning on farms. Point Blue Conservation developed methods in Excel spreadsheets to calculate and guide monitoring of perennial biomass. This can look like assessing hedgerows, windbreaks, and riparian forest buffers, or woody farm crops such as orchards and berry operations to see what their estimated carbon value is. To do these protocols, you will need a tape measure, DBH tape, and a clinometer or rangefinder to assess the site. Perennial biomass can also be estimated on an individual per species basis. The iTree tool has a MyTree assessment that has pre-assessed carbon benefits for many single tree species. Many species have been assessed. You can use these estimated carbon values to calculate the carbon benefit of the trees present on your planning unit. Herbaceous biomass is another on-site measurement that can inform your carbon planning and monitoring. This biomass will decompose quickly, or may be the cash crop that is sold and removed from the agroecological system. but continuing to monitor this metric can inform landscape productivity and help highlight what carbon is being removed from the system. Point Blue also has methods and protocols to measure this on-site. We've discussed some of the measurements that can be used in the field to inform carbon planning and management. Now we will briefly highlight a few tools that are freely available to determine when you should utilize these in-field measurements and how to develop monitoring plans. Point Blue Conservation has a plethora of resources to support your efforts for on-the-ground measuring and monitoring of carbon. They developed the Crop C Monitoring Handbook for using on cropland operations. They have sections discussing data quality and what is required to get the level of quality that your planning purpose requires. They have information on sampling plans to help you decide where you are sampling and how many samples you should take to meet your quality needs. They discuss carbon indicators and methods and practice-specific considerations. Range C is the rangeland complement of Crop C. It offers the same information through a rangeland lens for thinking about data quality, developing a sampling plan, and choosing indicators and methods, as well as specific management practice considerations. Web Soil Survey is another fantastic resource to reference to learn more about the soil properties and qualities that are present on your planning unit. They do have values for bulk density and organic matter present for soil map units. Map soil components do not always accurately reflect what is present on the ground. Getting on-site data is much more accurate and will reflect the management applied, but Web Soil Survey data can at least provide you with a value based on the soil type that's anticipated to be present in your planning field. The Web Soil Survey bulk density values can be useful to compare to your measured values, or when you can't measure bulk density in the field, you can use the Web Soil Survey bulk density values for estimating soil organic stocks. We'd like to thank the Washington State Conservation Commission as well as partner districts that participated in this work to put together these resources on carbon farm planning and develop the carbon farm plan template for Washington State conservation districts.